Okay, hello. My name is Sam Albert, and today I'm presenting our work, a new guidance technique for discrete event drag modulation for Aerocapture missions. I want to begin by acknowledging the lead author on this work, Ethan Burnett, as well as our advisor and co-author, Hans-Peter Schaub. To give an outline of what I'll talk about, I'll give an overview of Aerocapture itself, talk about some key challenges, and give an overview as well of the JPL Smallsat Aerocapture project that is providing the reference mission scenario for this algorithm development work. I'll give an overview of the current baseline choice for that project, Numerical Predictor-Corrector guidance, or NPC, and I'll go through how that algorithm works. And then I'll present our algorithm, the Quasi-Initial Condition, or QIC guidance, give an overview of how the algorithm works, give an overview of quasi-initial conditions themselves, and go through some of the different options for how this algorithm can actually be implemented. I'll show some numerical results that provide a proof of concept for QIC, as well as a performance comparison between NPC and QIC. And I'll end with conclusions and future work. Okay, so to quickly give an overview of what is Aerocapture, it's a method of orbit insertion, and it can be used as an alternative to a purely propulsive approach to orbit insertion. So this initial orbit might be a hyperbolic trajectory. It might be just a much higher elliptical orbit. And the spacecraft then performs an atmospheric flight pass. And so as it's flying through the atmosphere, the aerodynamic drag on the spacecraft reduces its energy such that at atmospheric exit, it is in a much lower elliptical orbit. And then at this first apoapsis pass, periapsis raise maneuver is performed to raise the periapsis out of the atmosphere. And finally, corrective maneuvers are performed as necessary to reach the final desired orbit. This is desirable because it reduces the amount of propellant required compared to propulsive orbit insertion, and potentially also reduces the total mass and cost for some destinations or scenarios. So although it is arguably flight ready, Aerocapture has never been flown on an actual mission. And additionally, it requires autonomous guidance, navigation, and control in an uncertain environment. So because the delivery state, aerodynamic properties of the vehicle, and in particular, the density as a function of altitude in the atmosphere are all uncertain, and it's difficult to accurately model or predict the atmospheric environment, some sort of closed loop flight control is required to successfully perform Aerocapture using the aerodynamic lift and or drag on the vehicle to achieve this. And finally, another challenge is that this atmospheric flight phase imposes some constraints on vehicle emission design. For instance, your satellite is now also required to be a hypersonic flight vehicle for some part of the mission. Having talked about Aerocapture generally, I'll give an overview here of the Drag-Modulated Smallsat Aerocapture project. That's a concept that's been under study by a JPL-led team, including contributions from NASA Ames, NASA Langley, and CU Boulder. And some of this work has been done in a simulation developed in JPL's Descends environment. And the goal here is to perform an Earth flight test of drag-modulated Aerocapture to retire risk and enable mission infusion of Aerocapture. And the hope is that these technology developments for the flight demonstration would also buy down the risk for future Aerocapture missions. So what I mean by drag-modulated Aerocapture is shown in this diagram in the lower right. There's some rigid drag skirt on the vehicle, and it is released at some point during atmospheric flight, changing the aerodynamic properties of the vehicle. And by varying when this drag skirt is released, the vehicle can target a specific desired final state. It can target a desired apoapsis at atmospheric exit. So the control over this Jettison time is the one-dimensional control authority that the vehicle has. On the left, I'm just showing some information about the vehicle itself. It would nominally use a deployable drag skirt such that it can be stowed in an ESPA volume for launch. After separation from the launch vehicle, it deploys this drag skirt, and as I described, uses it to successfully perform Aerocapture, after which the spacecraft itself can be deployed and used for its science mission. The guidance algorithm that is currently baselined for that Smallsat Aerocapture project is Numerical Predictor-Corrector guidance. I think it is fair to say that this is the state of the art for discrete event drag modulation, although that's not to say that other methods aren't out there. And I'll just go through this flow diagram of how the algorithm works. It begins with the simulation calling guidance, which is active as long as the acceleration sensed by the IMU is greater than some threshold value. The guidance then propagates from the current navigated state to atmospheric exit, releasing that drag cert at T sub j, the Jettison time, and then predicts the apoapsis error by simply taking that state at atmospheric exit, computing the apoapsis, and subtracting from that the target apoapsis. That provides an error. And if that error is, we check if the error is less than some tolerance, and if it is not, the Jettison time is updated and this process repeats. Won't talk much about how the Jettison time is updated, but it's essentially just a root finding process, and you can use bisection method or Newton's method. And so this repeats until error is below the tolerance, and once it is, the algorithm just checks if the Jettison time is greater than the current time, and if the Jettison time is already passed, Jettison is commanded, and then guidance exits. Okay, so one of the significant challenges for using an NPC algorithm is that this numerical propagation step is relatively computationally expensive, and it is performed at least once, but potentially multiple times in this loop where we're updating Jettison time. And additionally, it is difficult to bound the number of iterations that are required to guarantee convergence. You can do simulations and estimate how many it will take, and you can set a maximum number of iterations, but at the end of the day, it's hard to know for sure how many iterations it will take to guarantee convergence, and this makes it difficult to know before you get to implementation if your GNC hardware can actually run this fast enough to converge. And so one of the fundamental motivations behind the new algorithm that I'll present in a moment is, can we take this computationally expensive step and move it somewhere else in the mission that is less demanding on, that demands less rapid guidance turnover? Okay, so our proposed new method is quasi-initial condition guidance, and immediately one of its distinguishing features as compared to NPC is that it involves a significant pre-compute step. So this green shaded portion is performed only once and done sometime before atmospheric entry. We've been doing it at 10 minutes prior to entry because that is the time of the final navigation update to the spacecraft in this reference mission. And it also includes this purple shaded region that's performed every guidance call. So to go through this flowchart as well, we begin by rescaling density using some linear scaling factor k sub I on a nominal density profile. As an aside, this is not a very physical way of dispersing atmospheres, and it turns out not to matter very much for this algorithm because all we're really trying to do is generate a family of dispersed trajectories that smoothly vary. But I will also note that you don't have to disperse the atmospheres this way. You could disperse scale height, or you could do this in a number of different ways. It doesn't have to be using this k sub I method, but we've seen that that works fairly well for our implementation. Okay, so once we have this rescaled density, we, using that rescaled density, compute the optimal Jettison time using repeated numerical propagation. So this block is actually very similar to what the NPC algorithm does. It repeatedly predicts the apoapsis error and corrects Jettison time if that error is above some tolerance. So you can see already that we've taken that computationally expensive part and moved it to this pre-compute step. Once that optimal Jettison time is computed, we also numerically estimate the sensitivity of the Jettison time to the altitude, velocity, and flight path angle at atmospheric entry. And so this requires one or more additional numerical propagations in this step. And then we repeat this whole process for a range of K values, a range of atmospheric scale factors. And this, for example, might be ranging from 0.5 to 1.5. Okay, so once this pre-compute step is done, all this data, the time histories, the Jettison times, and the sensitivities associated with each reference trajectory is saved off. And then later, when the simulation calls guidance, and it's active because since acceleration is above the threshold, the guidance determines which of these pre-computed reference trajectories is closest to the navigated state at the current time. It then uses that information in some way to update the current value of the jettison time. And I'll talk more about that momentarily. And then finally, this part is the same as before. We just check if the current jettison time has already passed, and if so, command jettison, and then guidance exits. You'll notice again that there's no loop structure in this purple shaded portion of the guidance. And that's one of the things that makes it potentially computationally more efficient than the NPC algorithm. This is giving a little bit of detail on how we determine which of those reference trajectories is closest. Our heuristic for that, currently at least, is this distance parameter d, which is a weighted sum, taking into account the difference in semi-major axis and semi-major axis rate, comparing the current trajectory and each reference trajectory. So the reference trajectory with the smallest value of d is selected. And then I was very vague about how we actually update the jettison time using that information. And that's in part because there's a number of different options, and there's that I'll go through in a moment. And so you can do a 0th order correction, a linear correction, or some higher order correction. Before I get to that though, we should talk about what are these quasi-initial conditions that I've been mentioning in the name of the algorithm. And so looking at this diagram at the bottom of this slide, we begin with these blue dots, which are some dispersed series of actual initial conditions, and they are propagated forward using the true dynamics. This might be, the real simulation, it might be real life. And then at some time of interest t, we would have states at time t that result from each of those initial conditions. We then back propagate through some nominal model to recover quasi-initial conditions. We back propagate to the initial time. And so you can see that if the nominal model was exactly the same as the true dynamics, then these dots would be overlaid. The QICs would be the same as the initial conditions. But because our nominal model is some simplified model, let's say it only takes into account mu, J2, and drag, neglecting other aspects of the dynamics, these initial conditions will be a little bit different than the actual initial conditions. And so we call those quasi-initial conditions. And this, because we can always propagate forward or backward through this nominal model as desired, this is a complete state representation that effectively is a nonlinear coordinate transformation. And we're interested in this because QIC space is more linear than state space at time t for this application. What I mean by that is that a large distribution of states at time t becomes more compact when represented in QIC space, and this improves the accuracy of linear corrections. Okay, so having talked about what QICs actually are, how do we use the reference trajectory information to update jettison time? The first and by far simplest option is what we call a 0th order correction. And for this, we simply take the jettison time of that nearest reference trajectory and make that our current jettison time. So this doesn't require any back propagation. We can actually also skip the step of computing those sensitivities. All we have to do is pre-compute jettison time for each of the reference trajectories. The sort of next step up in complexity is a 1st order or linear correction. And so for this, we begin with the jettison time of that nearest reference trajectory and then make a linear correction using these pre-computed sensitivity values and also the current differences between the quasi-initial conditions for this actual state and the real initial conditions that were used to generate that reference trajectory. So to elaborate a bit on that, we take the current navigated state and back propagate through our nominal model to recover the quasi-initial conditions. And then the difference between that quasi-initial condition and the initial condition used to generate this nearest reference trajectory provides these delta H, delta V, and delta gamma terms. And so that allows us to make this linear correction. And so this requires us to pre-compute jettison time and all the sensitivity values for each reference trajectory. And finally, you could imagine doing something very similar to this, where you also back propagate to recover QICs and use that to get these differences, but then use some nonlinear interpolation technique, Lagrange interpolation or cubic spines or something like that to correct this reference value of the jettison time in some nonlinear way. And this requires pre-computing the Jettison time and, rather than the linear sensitivities, some nonlinear interpolation surface. So these are all valid ways of implementing what at its core is the same guidance algorithm. Okay, so I'm moving on now to the numerical results of our implementation, which currently is the 0th order correction method. That's because this is a proof of concept demonstration. And so we're showing what we can do with the absolute simplest option of how you can implement this guidance. So we use the descent simulation to perform a 5001 trial Monte Carlo analysis. And the key, a lot of things were dispersed in the simulation, but the key dispersions are density that is generated using EarthGram, as well as an entry flight path angle delivery variation with a 3 sigma value of 0.2 degrees. Like I said, we did this using the 0th order correction method, and those weighting factors, if you'll remember, in that equation for the distance parameter are set equal to each other at a value of 1. I'll quickly note that for stability, we also limited the change in the current Jettison value, Jettison time value to 5 seconds. So even if we commanded something greater than that, just cap it at 5 seconds in either direction. And for this, we were generating 85 different reference trajectories in this range. Okay, so the results, to be honest, were even better than we expected, given that we implemented the 0th order correction. We've shown that for this scenario, QIC achieves similar performance to the NPC for what is almost certainly lower computational effort. And a quick note on that, we don't have quantifiable, we have not quantified how much lower that computational effort is. We don't have, profiling data or any sort of hardware in the loop data. But because there's no repeated numerical propagation in the loop during the guidance updates, as long as you have enough memory for all those reference trajectories, I do think it's fair to say that QIC is lower computational effort than NPC. And so here we're just showing histograms comparing the actual apoapsis altitude. And so they're histograms comparing QIC on the left and NPC on the right. And then we're also showing this table also for the apoapsis altitude, showing the mean and standard deviation, as well as the 1st to 99th percentile bounds. This is significant error, and that's due in part to the fact that the dispersions on this current simulation result in some scenarios where the target is actually unreachable. And so both of these algorithms do what you would want them to do in those scenarios, which is command either releasing almost immediately or never actually releasing the drag skirt. But it results in a significant error because, like I said, sometimes you can't actually get to the target orbit. But this performance between this 0th order implementation of QIC and the existing NPC implementation is remarkably similar. So our key conclusions here are, as I've said a few times now, QIC and NPC were able to achieve very similar apoapsis targeting performance, even though QIC takes less computational effort. Although I'm also noting that it very likely takes more memory in terms of what's accessible to that guidance algorithm. We, in doing so, have demonstrated a proof of concept for the QIC algorithm, but I should emphasize that we have not stress tested this, so we haven't tested it on other scenarios or on much greater dispersion values, and so that's something we are interested in for future work. We'd also like to improve our implementation of the linear correction. We have initial results that show that it works well, and those are in the paper. However, it can sometimes be challenging to know autonomously whether that correction is actually in the linear regime, or if you're going beyond the linear regime and getting a correction value that's not actually correct or desirable. And partially for that reason, we would also like to explore possibilities that involve nonlinear corrections and think about how you might do that. And finally, could consider adjusting how those reference trajectories are dispersed. Because I talked about, currently we just linearly rescale density using a range of density scale factors, but there's a number of different ways you could do that, potentially by changing even more than one parameter. And so with that, if you're watching the recording of this, please feel free to email Ethan or myself with any questions. We'd be very happy to chat, and just want to acknowledge the many folks at JPL who helped make this work happen. Thank you.